Now let's take a closer look at how data is sent from one computer to another. We'll use the 5-layer network reference model as a guide, and we'll also employ the post office model we discussed earlier to illustrate some concepts. As you saw already, at each layer of the network reference model, specific information is added about what type of data you are sending and where it's going. Ultimately, your data is converted to electrical signals, transported over the network, and then processed by the receiving computer. Now let's examine what specifically happens in each layer, including which protocols are used. When you send an email, the email program on your computer, such as Microsoft Outlook, interacts with the application layer. Behind the scenes, the email program sends the message or data to your Internet email server for delivery. The email application uses the SMTP, or Simple Mail Transport Protocol application layer protocol, for this communication. Application layer protocols usually specify how data should be encoded, compressed, or encrypted, and how sessions should be managed. Some application layer protocols are shown on screen. Click any of the links on screen to learn more about each protocol, or click the Continue button to continue with this topic. Using our postal mail analogy, our data at this point is like a letter, written in a language the recipient understands and following common conventions for letter writing. However, our data does not yet have an envelope specifying where it should be sent. The application layer sends the data down the stack to the transport layer. The transport layer specifies which application layer protocol should be used to process the data once it arrives on the receiving computer. Each application layer protocol is assigned a unique numerical identifier called a port. Note that this port is a software port, not a hardware port. For example, HTTP uses port 80, DNS uses port 53, and SMTP uses port 25. This destination port number is analogous to the recipient's name on our envelope. Just like there might be multiple people living at a single address, each with a unique name, multiple programs might be running on the destination computer using different application layer protocols. Each application layer protocol has a unique port number, so incoming data can ultimately find the correct program. The transport layer includes the destination port number in the header it adds to the data. When the data arrives at the destination computer, the transport layer there examines this number to determine the application layer protocol the data should be sent to. The transport layer on the sending computer also includes a source port number in the header, which is similar to the name in the return address. The source port number, typically a random number, uniquely identifies the connection on the sending side. This port allows the receiving computer to carry on multiple sessions with the sending computer without intermixing the data. Beyond identifying the destination and source port numbers, the transport layer has a second important responsibility as well. Again, let's consider our letter. When you are ready to mail your letter, you have a choice to make. You can simply add a stamp, drop it in the mailbox, and assume it gets there. Or you can request a return receipt, which the post office returns to you upon delivery, so you can be assured it has arrived. As its second responsibility, the transport layer offers a similar choice for reliability. The User Datagram Protocol, or UDP, and the Transmission Control Protocol, or TCP, are two transport layer protocols in the TCP/IP protocol suite. UDP and TCP are also known as Layer 4 protocols because they take place in the fourth layer, the transport layer. UDP is a very simple and fast protocol. UDP is a best effort delivery service providing no delivery notification, error checking, or recovery procedures. It's exactly like dropping your envelope in a mailbox and hoping for the best. With UDP, the sending computer doesn't know if the receiving computer actually received the data. Applications sending short messages or time-sensitive data such as DNS online gaming, voice over IP or VoIP, and streaming video applications like IPTV often use UDP because speed is critical. Voice and video applications are designed to handle occasional packet loss without a major impact on performance. For example, you might see a video jump, or you might miss a word in a phone call. Sometimes you might not even notice a problem. When you type a URL in your web browser, behind the scenes you're using DNS to find the IP address of the web server. DNS must operate quickly, and most of the time you receive a quick DNS response. But if for some reason you don't receive a DNS response, no harm done. You can simply try to access the web server again later. TCP, on the other hand, is a more robust protocol, providing delivery notification, error checking, and recovery procedures. With TCP, the receiving computer tells the sending computer when the data was received. It's equivalent to sending our letter by registered mail with a return receipt. HTTP, SMTP, and FTP all use TCP. TCP accepts data from the application layer protocol and cuts the data into smaller pieces called segments to ensure a steady flow of data between two computers regardless of the differences in connection bandwidth. Segmentation is like taking our letter and sending each page in a separate envelope. By numbering the pages, the recipient can place the pages back in order. Likewise, TCP assigns a sequence number to each segment. On the receiving side, TCP uses the sequence numbers to put the segments back together in the correct order. The receiving side uses the sequence numbers to tell the sending side when segments have been received, just like the return receipt in our postal analogy. If the sending side does not receive an acknowledgement within a reasonable amount of time, it resends the segments. Once this process is complete, the transport layer sends the data or segments down to the network layer, which is also known as Layer 3. The network layer takes a segment and adds a header to create a packet. The Layer 3 header contains a destination and source internet protocol or IP address. You'll also hear these addresses referred to as Layer 3 addresses or logical addresses. Layer 3 addressing can be compared to adding your recipient's address and your return address on an envelope. We cover IP addressing in much greater detail later in the course. Notice that the network layer treats the data it receives from the transport layer as one piece of data. It does not need to inspect the transport layer headers or the original data during the encapsulation process. As part of its own headers, the network layer adds a number identifying the upper layer transport layer protocol. Each transport layer protocol is assigned a unique identifier or IP protocol number. For example, UDP is IP protocol number 17 and TCP is IP protocol number 6. When you send an email, the sending computer uses TCP as its transport layer protocol. When the sending computer adds the Layer 3 header to the data, it identifies the IP protocol number as 6. When the receiving computer unwraps the data layer by layer, the network layer examines this IP protocol number to determine which upper layer protocol should process the data next. Because in this example, the IP protocol number is set to 6, the network layer on the receiving computer sends the data to the TCP protocol for further processing. The next layer down the stack is Layer 2, which in our 5-layer model is called the data link layer. Layer 2 receives the packet from the network layer and, like the layers above it, adds its own header to the packet to create a frame. The header usually includes another address, commonly referred to as a Layer 2 address, a physical address, or a media access control or MAC address. This address is different from the IP address or Layer 3 address added by the network layer. It can be compared to the addressing on the post office's sorting containers we saw in an earlier section. We explain this analogy in more detail in the next section. The Layer 2 header typically also includes an indication as to which Layer 3 protocol is in the data portion of the frame. Layer 2 also performs its own data integrity check so that corrupted or damaged frames are discarded as early as possible in the transmission process. This check is done by adding a checksum in the trailer at the end of a frame. A checksum is the result of a mathematical calculation. The sending computer runs the computation and inserts the checksum into the frame's trailer. The network device receiving the frame runs the same calculation. If the computation results match, the frame is accepted. If they do not, the frame is discarded. Finally, Layer 2 converts the data into a format that the physical layer can understand, the ones and zeros of digital communications. The physical layer, or Layer 1, converts these bits into electrical signals and sends them across the physical medium, which can be a telephone wire, a fiber optic cable, or even a wireless environment. Physical layer specifications define characteristics such as cabling specifications, voltage levels, physical data rates, maximum transmission distances, and physical connectors. In our mail analogy, the physical layer is like the mail truck, airplane, or train that carries the letters from post office to post office.